Okay, guys, so now that we've spent some time working with projectiles that were launched horizontally, that is parallel to the ground, I want to think a little bit now about what would happen if you had a situation where a projectile was launched at an angle. So, for instance, to get us started here, let's imagine here's the ground, and maybe we have some sort of a cannon that's firing a projectile, firing a cannonball or whatever. So here's the cannon, and it's firing the projectile, you can see here, at an angle with respect to the ground. In other words, it's not going parallel to the surface of the ground, it's going up at an angle. And let's just say for this problem, that angle will be 35 degrees. And the velocity, the total speed that the thing is launched at, let's make it a big speed, 450 meters per second. That's a pretty large velocity. And now we could ask ourselves, of course, we know what's going to happen, I think. This cannonball is going to do something like this. It's going to do its little parabolic arc, and it's going to travel some distance, delta x, some horizontal distance. Sometimes we call that the range, right? That's the horizontal distance. And it's also going to go up a certain distance, a height. We call that delta y. And I might ask you to calculate the delta x and the delta y for this particular case. In other words, if I fired this cannonball 450 meters per second at a 35-degree angle, exactly how far does it go horizontally, and how high does it go? What's the maximum vertical distance it gets? Um, and we're going to work through this now, and what we have to realize immediately is that this velocity, 450 meters per second, part of it is acting in the x direction, and part of it is acting in the y direction. So the first thing I'm going to do is take that velocity, and I'm going to split it up into its components. That velocity has a x component, and it has a y component. There's a v sub x, and there's a v sub y. And the first thing I'm going to do is to go ahead and calculate those velocities. Let's remember that the velocity here, this is 450 meters per second. And let's also remember here that this angle is 35 degrees. And now hopefully we remember from our discussion of vectors that using the 35-degree angle, I can calculate v sub x and v sub y using sine and cosine. So in particular, v sub x here is going to be 450 times the cosine of 35 degrees. Double check that, and I think you're going to find that that's about 369 meters per second. V sub y, that's 450 times the sine of 35 degrees. And that gives me 258 meters per second. Hopefully you're understanding how I'm getting sine and cosine of that angle there, and what I'm doing to find the two components. So now that I've split the vector into its components, I now know that as this cannonball is traveling, it begins with a vertical speed of 450 or 258 meters per second. That's how fast it's going vertically. And I know, of course, according to my projectile rules, that that velocity is going to change at the rate of -9 meters per second per second. The x velocity for this projectile is 369 meters per second, and I know that that will remain constant throughout the problem. So let's first try to think about how far this projectile is going to go. How far would it go? And to do that, the first thing we need to figure out is how long it's going to be in the air for. I know it's going to go this speed, v sub x, the entire time it's in the air. But how long is it in the air for? So let's go ahead and find t. Now you might remember when we were doing horizontally launched projectile problems, the thing that determined the time was the height, the delta y. And in this case, it's a little bit different than that, of course. We're still going to use the delta y equation in the classic way, but it's a little bit different because we don't have a situation where you're starting at a certain height and the object is simply dropping. Here, the delta y is 0, right? If I take a look at the problem, the cannonball begins at the ground and ends at the ground. So what I can say here now, I'm going to use my delta y equation here. I'm going to say delta y equals 0. Make sure you understand why that is. And that's going to be the initial y velocity, which is no longer 0. In the horizontally launched projectiles, v initial in the y direction was always 0. It is not now. V initial in the y direction is now 258. So I say 0 equals 258t plus 1/2 negative times negative 9.8 times t squared. Now I can go ahead and solve for t. So I get 0 equals 258t minus 4.9t squared. By the way, note that I'm making this initial y velocity positive, and that's because the initial y velocity is positive. It's up, it's vertical, right? That's a vertical velocity, so it's positive. Now I can go ahead and solve for t. I'm going to get two values for t. When I go ahead and solve for this, I get t equals 0, of course, and then the other t value that I get is 52.7 seconds. Make sure you understand how I got from here to here. If there's any questions on that, let me know. Now, what does this mean? The 0 and the 52.7, these are the times that the cannonball's at the ground, right? It's at the ground at t equals 0, of course, that's when we begin, and then it's at the ground again, it lands after 52.7 seconds. Which means that the cannonball is going to be in the air for 52.7 seconds, about 53 seconds. And the entire time now, it's going this speed that entire time. So now I can go ahead and solve for delta x. Okay, my delta x equation, constant velocity equation, v sub x times t. V sub x, v sub x now is 369, that's v sub x. And t is 52.7. So it's a simple calculation now. Calculate that out and you get this really large distance, which is 19,000 meters, or 19,429 meters. That's a great distance. It might seem a little bit unreasonable, but keep in mind that, first of all, this is a huge velocity. 450 meters per second is huge. And also bear in mind that this is not accounting for air resistance. You'd get a much smaller answer if there were air resistance. So work through that, see if you can follow what I've done, make sure that you can redo or reproduce what I've done on the in this problem. And again, if there are any questions in class, we can go over it. The second part of the question, so that's only half of the problem, you might remember I also asked, how high does it go? In other words, I asked you to try to find delta y. So to find delta y, now I'm going to go over to a new sheet in just a second here, but to find delta y, I now need to figure out how long is the cannonball in the air for. Now, some of you might have already realized that it's just going to be half of the time we found right here. We found that it's going to be in the air for 52.7 seconds, and you might realize that it's just going to be half of that time. That is true when and only when delta x equals 0. In this case, it'll work, but in other cases, that won't work. So let's make sure that we do know how to find the t to the very maximum height point. And you might realize that, actually, let me go back real quick. You might realize that at this point, at the maximum height, v sub y equals 0. You might have realized that. We're going to use that fact now to figure out the time it takes for the cannonball to get to the top. So how do I do that? Well, I use my equation v sub y equals v initial y plus gt. V sub y is 0. That's at the very, very top. It's 0. The initial y velocity, which I found before, that initial y velocity is positive 258. G is negative 9.8 times t. And indeed, I do get this t value of 26.3 seconds, which is half of the total time that we found previously. So no surprise there. That's the t value. So now how do I find the height that corresponds to that t value? Well, I'm just going to use my delta y equation. Delta y is the initial y velocity right here, 258, times t, 26.3, plus 1/2, negative 9.8, times t, 26.3 squared. do that calculation, you should get 3,396 meters. Go ahead, and that's positive, of course. Um, Go ahead and double check that. Um, Again, really 3 kilometers, that over 3 kilometers, that's an enormous height. But given large velocity and no air resistance, that's how high the object would go. Some of you may have already realized that there's another way you could have calculated this and saved yourself a step. You might remember this old equation that we used to have: v final squared equals v initial squared plus 2 times a times delta x. You could use this equation. This delta x then would be what we are now calling delta y. V final is 0, V initial is this value, 258, acceleration is negative 9.8. So you could have adapted this equation to projectile motion, and it would have saved you a step. But I've sort of shown you the classic way to do that problem here. All right, so that's a rather quick review of how you deal with these problems where you have a projectile launched at an angle, and it's this step right here, I think, that's critical. Remembering how to take your velocity and split it up into its components, its x and y velocity. Hopefully you've understood how I've done that and how I've used those velocities. Last thing I'm going to do here is I'm going to leave you with a problem. I'm going to give you the problem, and I'll give you the answer, and I'm going to ask you to solve it and see if you can figure out how to solve it. So here's the problem. I'm going to imagine that I'm on the top of a building. Let's say it's a 25-meter high building. Here I am on the top of this building, and I'm going to throw something up. I'm going to throw this object up at 12 meters per second. I'm going to throw it at a 20-degree angle. Hopefully you can read this picture. It's not the best picture. That's supposed to be 20-degree angle. So it's 12 meters per second is the initial velocity, and it's at a 20-degree angle. I'm on the top of this 25-meter high cliff or building, and of course you're going to get this parabolic arc. Notice now, I'm just going to sort of hint to you, the delta y does not equal 0. That's going to make the math slightly more involved in this problem. And the question I'm asking here is, how far does the object go? In other words, I want you to find this distance delta x. What is that delta x from here to there? I'm going to leave you with that. Try to solve it. A little bit more math. You're going to probably going to end up with a quadratic in there. You should finally get, for your answer when you're done, you should get an answer of about 30.5 meters. So I'll leave you with that. Good luck trying to solve that. Hopefully it works out for you. And we'll begin with this next class.